go to the next speaker, who is Jim Halverson. Maybe James can share.
I'm happy to start early. I guess I'm supposed to start in 4 minutes, but I'm happy to start early if people are looking for that. Hold on. You see my screen?
Yes, but maybe you want to go like full screen instead of because we see like.
Yeah. Here, let me see if I can figure this out.
Yeah, now.
I want to try to fix the aspect ratio though. Let me see if I can do it. Nope. All right, I'll live with it. Is the aspect ratio okay?
Well, the problem is maybe do you have like pictures or something which may get screwed with this, or I mean?
No, I think it's fine. I think it'll just have the black bars on the side.
In my screen, it looks great, but.
Okay. Yeah.
Good. So our next speaker is Jim Halverson from Northeastern, and he's going to tell us about statistics and symmetries of neural networks and quantum fields. So please take it away.
All right. Thanks to the organizers and especially to Jan for inviting me to give this talk. It is nice to see all of you virtually. I hope at some point we can be together in person again. Hopefully once this surge is over. So today I'm going to tell you about statistics and symmetries of neural networks and quantum fields. This is based on work with my students Anandita Maidi and Keegan Stoner. And they are wonderful. Anandita will be applying next year for high energy theory postdocs, so keep an eye out for her. And if you happen to be in the machine learning industry, Keegan will be looking for jobs this year. So, right, so I started a few minutes early. This talk is a little light on slides to try to aim for more colloquium and paced discussion. And I appreciate that I'm at the end of the day, so thank you for sticking with me throughout this. So, what's going on in this talk? What is it that I'm trying to achieve? What am I after? Well, what I want to point out and remind you of, and I'll pitch it at a broad audience, is that neural networks and quantum field theory are the backbones of artificial intelligence and physics, respectively. But we also all like math. That's part of why we're here. And their common backbone, neural networks and quantum field theory, is statistics. And so I'd like to tell you a little bit about the statistical underpinnings of both of these, and then I'll try to unite them under some common framework where, in particular, you can use ideas from quantum field theory to try to study neural networks. And ideally, neural networks are also going to teach us something fundamental about quantum field theory. So the quick sketch of my talk is, first, I'd like to go over what is a quantum field theory. I see a lot of my friends in the audience who know this very well. I don't know that I'm going to say anything new to you here, except perhaps to remind you that quantum field theory, in terms of perturbation around Gaussian fixed points, it relies crucially on Gaussian integrals and their connections to Feynman diagrams. Then I'll talk about what is a neural network, and I will say some things in ways that maybe you haven't heard them before, thinking about things in a statistical framework. Then I'll talk about how they're related. And then I'll talk about what are the symmetries. Since we're going to talk about neural networks being related to statistics, we'll want to know about the probability density over functions associated with a given neural network architecture. And if you have that language, you might ask, what are the symmetries of a neural network probability density? And I'll give you a way to do that via duality. So, and there's a little bit at the end, if time permits, that I might have a chance to tackle regarding preserving symmetry during training, and another way to break Gaussian process limits that is not the traditional one that's studied. So what is quantum field theory? Well, a broad overview is that quantum field theory is a quantum theory of fields and their particle excitations. Quantum field theory is not just for fundamental particles, such as the Higgs boson and the Standard Model. It's also for condensed matter physics and quasi-particles, for instance, in superconductors. A single quantum field theory does things like predict radioactive decay rates, the strength of particle scattering, etc. And at least as canonically taught in quantum field theory courses, there's sort of two main perspectives. One is called canonical quantization, which is an approach that takes the Bra-Ket approach of Dirac, and quantum mechanics is sort of front and center. But today I'm going to view things from the point of view of Feynman's path integral. And of course, this is a subject for which there are many Nobel Prizes. It's pretty easy to rattle off 5 or 10 Nobel Prizes in physics associated with quantum field theory in some way, shape, or form. And one of the more recent ones has to do with the discovery of the Higgs boson, which I remember vividly on July 4th, 2012. This particle was discovered by the Atlas and CMS experiments at LHC. It was the final particle, not article, in the standard model of particle physics that hadn't been discovered. And at least at the time, it was hard to imagine in the US what might constitute better science press. This was 4th of July, Independence Day in the US, New York Times front page above the fold press. And this was extremely exciting. And in 2013, a theory Nobel Prize went to Higgs and Glare. Sadly, because of the details of how Nobels are awarded, the experimentalists were not awarded a Nobel, but I think all of us physicists recognize that they also deserve one. So, okay, so that's quantum field theory. And what I want to remind you is that when I draw a little diagram like this, which is a Feynman diagram, I want to remind you where this comes from a statistical perspective. And in particular, this is a particular, okay, so you have over here, time goes to the right. You have some process that produces the Higgs boson. It could be gluon fusion or vector boson fusion. And this describes a decay of the Higgs to a loop of top quarks, which then decay into 2 photons. This is called the diphoton channel. This is one of the discovery channels for the Higgs at LHC. But this is a Feynman diagram, and let's remind ourselves where these come from, because at a basic level, it's just related to near Gaussian statistics. So pictures, Feynman diagrams are pictures that are useful for computing moments of Gaussian or near Gaussian distributions. Here's how it works. Let's just take a standard single variable Gaussian distribution. This is the 2nth moment of that Gaussian distribution. It's represented by this ratio of integrals here. In physics language, you can think of this as the partition function down here. And this 2nth moment of the Gaussian distribution is 1 over a to the n, 2n minus 1 double factorial. And this is not something that people necessarily know before you tell them, but this factor here, which is 2n minus 1 times 2n minus 3, et cetera, all the way down to 1, this factor is the number of ways to connect 2 endpoints in pairs. And so if I just hand you this expression, and this is this factor here is the number of ways to connect 2 endpoints in pairs, and notably this is 1 over a to the n. If you connect 2 endpoints in pairs, there are n edges between those 2 endpoints. And so you could come up with a rule for a way to write pictures that allow you to reproduce this, this answer together with the combinatoric prefactor. And the rules are that for every, you write down all ways of connecting 2 endpoints in pairs, and you sum them up. And in the analytic version of that graphical expression, for every line, you draw a 1 over a, and then you sum things up appropriately. So the 4th moment is this diagram plus this diagram plus this diagram, which under these rules for mapping pictures to expressions, we write as 1 over a times 1 over a plus the same thing plus the same thing, which is 3 over a squared, which is this 2nth moment evaluated in the case that n is equal to 2. Okay, so this is where Feynman diagrams come from, fundamentally speaking. Of course, this is just pure statistics, but this is underlying what's happening in quantum field theory. Crucially, we can compute the 2nth moment of a Gaussian exactly. We cannot do it for a close to Gaussian distribution. But what I want to point out is that you can do this in perturbation theory. So if you compute the 2nth moment of the close to Gaussian distribution, where I made lambda small, I turned on some non-Gaussianity in the distribution here. And then if I do a series expansion in lambda, what I end up with is an expression like this. Here I have used our old trick called multiplying by 1. And in this expression, which is a perturbation series for the 2nth moment of the near Gaussian distribution, I will point out that this here over this is the 2n plus 4kth moment of the Gaussian distribution. And this denominator over this numerator gives you the 4kth moment of the Gaussian distribution down here. For some small lambda, what we do conventionally in physics is we truncate it. And what we have is a way to some order in perturbation theory in lambda, we have a way to represent moments of the non-Gaussian distribution in terms of moments of the Gaussian distribution. But because we have a diagrammatic way to write the moments of the Gaussian distribution, I have a way to approximately write in terms of diagrams the moments of the non-Gaussian distribution. Okay, So of course, in physics, additions and extra widgets may arise. That is why quantum field theory is non-trivial. It's not just this, but this is the backbone underlying diagrams in field theory. So the essence is to approximate non-Gaussian moments in terms of Gaussian moments diagrammatically. So roughly, it sounds like quantum field theory is physics widgets on top of a statistics backbone. And I think that that is fundamentally true. The widgets are very important, but this is what's really at the heart of it. So statistically speaking, quantum field theory is defined by a distribution on field space, the so-called Feynman path integral, and the log probability S of phi is what we call the action. So here's the partition function. I'm going to be in Euclidean throughout. That's not crucial to what I'm going to say. And this e to the minus s phi is the density over functions. S is the action. And so if you take the negative log probability of this, you get the action back. There's various things you can measure experimentally. One thing are the endpoint correlation functions associated to the density over functions that defines the field theory. This is the endpoint correlation function. It's just the expectation value of phi of x1 through phi of xn evaluated in this density. Okay. From this perspective, as you know, free quantum field theory is a case that has Gaussian action, and I'll write some down in a second. And that's a case where you can A, solve the theory exactly. You can just compute all of these moments exactly. And B, it's a case where there are no interactions. On the other hand, what we normally do in perturbative quantum field theory, we don't perturb around an arbitrary theory that we care about. We normally perturb around free field theory. We perturb around the Gaussian case. So the distribution in that case is close to Gaussian. It would be the free theory action plus some higher non-Gaussianities. And we compute the approximate moments perturbatively. That is, we compute the correlation functions of the interacting theory in perturbation theory using techniques that are effectively equivalent to this. Okay. So quantum field theory is physics widgets on top of a statistics backbone. That's what I want to point out. On the other hand, you might ask, what is a neural network? Okay, well, I want to emphasize before getting into what it is, that these are important. That what has been happening in deep learning in the last 10 years, as we have already heard extensively at this conference, is a big deal. And all of us that are talking on this subject are putting up various computer science results on our screens, hoping that they can motivate some of the things that we're doing to try to make breakthroughs in math and physics. So in particular, there's at least 4 different types of deep learning out there, and neural networks are the backbone of all of them. So first of all, there's supervised learning. In supervised learning, this is the most common kind when people first learn about deep learning. The neural network is a powerful function that predicts outputs, such as class labels given an input. So if I give the neural network that image and that image, we recognize them as both 3s, but it needs to learn how to say that it's a 3 with high probability. We've heard in some talks at this conference, including Andre's nice talk this morning, about reinforcement learning. In this case, the neural network is a powerful function that picks intelligent state-dependent actions. We know that presented with a slate of possibilities at any given point in time, if our distribution on that slate of possibilities is random or arbitrary or uniform, it generally leads to subpar results. And what we're doing in life and what we try to teach our kids to do is to update their probability distribution on actions given the state so that they have good rewards, good behavior. That's how reinforcement learning works. But crucially, that probability distribution on actions is represented by a neural network. I won't talk about natural language today. Maybe I'll mention that there's generative models. In this case, the neural network's a powerful function that maps draws from a noise distribution to draws from a data distribution. So this is an output of a vector quantized variational autoencoder 2 that has been trained. And this is an image of a person, but this person actually doesn't exist. So the neural network in this case is powerful in the sense that it takes Gaussian noise draws, produces images like this. And if I put this person in a lineup of 100 images and I asked you to pick the fake person, you wouldn't be able to do it. It's pretty impressive. Okay, so that's why we care. Neural networks, more broadly, we're going to talk about them from a technical perspective and connect them to statistics. Neural networks are powerful functions. So a neural network is just the function. Here, it'll be from R to the D in to R to the D out for us. It's a function with continuous learnable parameters theta these are the things that get updated in the training process to be able to perform better. And it sometimes has some discrete hyperparameters that are chosen at the beginning of time before training to be, that are fixed forever. And those are part of what defines the architecture. And in our case, we'll have one important discrete hyperparameter, n. So training updates data to improve performance. And crucially, what I want to remind you in this context today is that theta here, if I fire up my code, theta, these parameters are drawn from some distribution on parameter space. So these are draws from some parameter distribution. Okay. Great. So keeping this in mind, that our neural network's a powerful function with some parameters theta that are drawn from some distribution, think about actually trying to do something with these. We do this in all of our machine learning applications that use neural networks. You fire up your code and you have it create neural networks, some neural network. But crucially, because the parameters that are appearing in the neural network when you fire up your code are drawn from some distribution, this neural network is a random function. And so if you restarted your code, if you did it again, you would, unless you got extremely lucky and drew exactly the same parameters, you would get another random function that's different from the random function that you had the first time around. And you could do this again and again and again, and they would all be different random functions that are constructed in your code, and then you could train with different ones, right? So when we talk about neural networks being random functions, we should be asking ourselves, from what distribution? Normally, we think of neural networks as having an architecture with random parameters. But from this perspective that I just pointed out, they're also random functions, and you could imagine studying them instead in function space. And I'll say what that means. Before I get there, I want to revisit a central question in machine learning from this point of view that the distribution matters, the distribution over functions matters. So in distribution language, I want to ask, what is learning? We're talking about machine learning a lot at this conference. So what is learning from this different perspective? So here I have a cartoon of function space going to the right. And I'm going to say, fire up your code, and a little red dot is going to drop down. And this is your randomly initialized neural network. And because you know how to do this, you train your code on some data, and training begins. And the green network goes somewhere in function space, and then it comes somewhere else, and it converges, and it lands you at exactly this point here. So this randomly initialized neural network has passed to this trained neural network via the training process, whatever it may be, whether it's gradient descent or natural gradient or Bayesian inference or whatever. Okay. So what happens in this process is that the first randomly initialized network becomes the trained one. But you could do it again. You could fire up your code again. 2 would be mapped to the second trained network, and you would continue to map randomly initialized networks and train them, and they would go somewhere else in function space. And the point is that what is fundamental here is not any one of these individual neural network draws or where it lands up after training. What is fundamental is the distribution at initialization, the distribution of functions at initialization, and the train distribution. Okay. So learning is the process by which the distribution at initialization turns into the train distribution. In physics language, learning is a data-induced flow from an initialization function-based distribution to a train distribution. If you're training with Bayesian inference, you can cast it in the language of Bayesian statistics and say that learning is approximating the posterior over functions given a prior or likelihood in the data. Okay, so this is the distribution perspective. And I wanted to mention that in some sense, this is the fundamental thing, not any given particular neural network draw. Okay, so returning to this question, from what distribution, we normally think of neural networks as having an architecture with random parameters. But as we've emphasized, they're also random functions, and we can study them instead in function space. But I already emphasized to you that quantum field theories are defined by densities over functions as well, and which maybe suggests that in some sense, neural networks are equal to quantum field theories. And of course, one has to say more to make that any kind of non-trivial equality. But what we want to try to do is unite them via their common statistical backbone, and ideally use one to understand the other. And you would hope that the quantum field theories, if we're going to make this precise, that the quantum field theories that we usually know and love have some property that some of the neural networks that we know and love have, so that you can use some of the techniques here to approach this. Okay. So this question that we asked is, what distribution are these drawn from? What I want to do is sharpen this idea with the simplest possible example. So a single layer feed-forward network is the simplest example of being able to get a handle on what distribution the neural network is drawn from. This is a result of Neil from his PhD thesis in the 90s, which was trying to connect the worlds of artificial neural networks and Bayesian statistics in a particular way. And that's what he did. So let me tell you how this classical story goes. In this case, my neural network is a single layer feed-forward network. It maps from R to the D in via some weights and biases that are drawn from some distribution into Rn. A nonlinearity acts element-wise, which of course preserves you in Rn. And then you map it down to some output dimension with a linear layer with some weights and biases also drawn independently from W0 and P0. So concretely, this is just the function. So you draw these W's, W's are matrices and B's are vectors. You draw these matrices and vectors from some distribution, and what the function is W0 times X plus the bias vector, act with the nonlinearity, act with W1, and add the last bias vector. This just is the function, okay? The limit that we're interested in to try to make quantum field theory and neural networks touchier and to try to make precise which distribution these neural networks are coming from is the limit of infinite width. And this limit of infinite width is the n goes to infinity limit. And what I want to point out is that when this is happening, this matrix here has dimension d out by n, because it's multiplying this n vector that is in here. So as n goes to infinity, what this becomes is a d out by infinity matrix. And each of those d out entries, compared to what's happening here, is taking this matrix and adding up an infinite number of independently and identically distributed entries from this W1 matrix. And this is precisely, assuming that you choose an appropriate distribution to draw parameters from, this is precisely the case in which the central limit theorem applies. And the reason that this is relevant is that it means that the output is drawn from a Gaussian distribution. And this has a particular language in statistics. The language is that the neural network is drawn from a Gaussian process, which for physicists, we should just say that that's just a Gaussian function space distribution. Okay. Now, this is some very simple architecture. This is some classical thing. And of course, being people who want to come up with theories that explain more than just one particular thing, one would hope that this phenomenon of a neural network being drawn from a Gaussian process in some infinite n limit, one would hope that that's a more general thing. And that's something that since the 1990s, it was actually dormant for about 20 years. But since the 1990s, there are more and more and more results showing that neural networks with some fixed architecture are drawn from a Gaussian process. So the classic result is this single layer infinite width feed-forward network, but deep infinite width feed-forward networks are also drawn from Gaussian processes, as are infinite channel convolutional neural networks. And many of us know Greg Yang at Microsoft Research. He has tried to unite all of this under a common framework that he calls tensor programs, and tensor programs allow you to show that all of the architectures in this little blurb are drawn from Gaussian processes. And it's actually not that surprising, because the mechanism that made it true is just that I added up an infinite number of IIT entries and I applied the central limit theorem. So any architecture that does that roughly is going to be drawn from a Gaussian process.
James, can I interrupt you? There is a question in the chat.
Sure.
So can you say something on the kernel of the Gaussian process?
Sorry. Can you say something on the kernel of the Gaussian process? Yes. I think I have examples in the backup slides, but basically it can always be computed in parameter space, Sven. I can say a lot of things. Can you maybe specify your question a little more?
Yeah, like to have an intuition for the dependence on, say, the activation function and so on.
Yes.
So I mean that plays a role in some sense, and also you make some choice in the sense of, for instance, the choosing the initial initialization distribution, how the kernel depends on
That's right.
these and so on.
Yeah, that's right. So I think you know what, I'm gonna look forward to my slides so I can see if I can answer that question based on what's actually in my slides. I can't. I think it's in the backup. Let me check. Let's see.
Yeah, we can also discuss this later.
Yeah. None of this illuminates the issue at the equation level. So let me say what the answer is in words. The answer is that parameter space gives you a way to compute the expectation value in some parameter distribution of f of x1 times f of x2, where f is the neural network, right? And so the details of the activation function, which you asked about, appear in the structure of f, and the details of the parameter distribution appear in the expectation value that you're computing. So you're integrating f of x1, f of x2 against the parameter distribution, where all those parameters appear in f of x1 and f of x2.
So here's my question in the sense. I mean, you can measure this empirically.
Absolutely.
But to what extent can you do things analytically?
Oh, yes. It's a question of whether you can actually evaluate the integral associated with the expectation value. And in all the cases I just flashed at the end, you can do it. Right. So it's really a question of whether you can evaluate the integral. You can always write down an analytic expression for the integral. It may be complicated, but usually when you say something like have analytic control, you mean that you don't just leave some complicated integral, you actually try to evaluate it.
Sure. I mean, you want to calculate the path integral. I mean, oh.
Right. So the integral that I just said is not the path integral of the Gaussian.
Yeah, I know, I know. But in some sense, the equivalent of saying,
yes.
Okay, you're able to do it.
Yeah, that's exactly right. Maybe it's worth saying that there are some papers where the like Joshua has some papers where the kernel is not evaluated analytically, but they do it empirically and they do various tests that way. So yeah, there's different ways to do it. Yeah.
Thanks.
Good. Another thing to mention is that not only do many architectures admit this limit, but under Bayesian inference of the Gaussian process or under continuous time gradient descent with mean square error loss, either of those will take a GP and during training preserve the GP property. So this nice property, which we'll abuse many times in this talk, actually persists under training, appropriate types of training. Okay. So free field theory is a Gaussian process. And so infinite neural networks are kind of like free field theory. This is free field theory. It's e to the minus s, where s is this particular thing that physicists know and love. It's phi box plus m squared phi. This is the double derivative. And you know, so in this context, free field theory is a Gaussian process that happens to be translation invariant and local. And statistics entirely determine, the statistics are entirely determined by the 1-point function, the mean of the process, and the 2-point function, which Gaussian process people call the kernel, physicists would call it the propagator, whatever, they're words. And so what we do is we compute the correlators in terms of Feynman diagrams in exactly the sort of way that I alluded to. So here's an example. This is the 4th moment of the Gaussian process. So this is just the expectation value of f of x1, f of x2, f of x3, f of x4. In the case that f is drawn from a Gaussian process, it simplifies into this sum of products of kernels. And the Feynman rules here are basically anytime you have k of x1, x2, draw it as a line between x1 and x2. And so this set of Feynman rules is reproducing, sorry, these Feynman diagrams via the Feynman rules give you this set of kernels, just like in field theory. But you know, what about finite n networks? So the function space distribution is generally non-Gaussian. It is generally non-Gaussian at finite n. But crucially, at infinite n, because you get the functions are drawn from Gaussian processes at infinite n, what it means is that the non-Gaussianities have to go to 0 as n goes to infinity for any of these neural networks that are drawn from Gaussian processes. So what that means is that if n is large enough but finite, the non-Gaussianities are in some sense small, and one can be more precise about their suppression in 1 over n. And what that corresponds to in physics is turning on interactions. That at large but finite n, if your neural networks are drawn from distributions that have small non-Gaussianities, you should do perturbation theory just like I showed you in that sort of first slide earlier on. And this corresponds to weakly coupled interactions. So the sort of punchline of our first paper is that finite n neural networks that admit a Gaussian process limit are drawn from non-Gaussian processes where the non-Gaussianities are small. And so you could do some neural network phenomenology. You could try to write down some non-Gaussianities and then see if those non-Gaussianities, either theoretically or experimentally, if they reproduce the correct correlation functions to some order in perturbation theory. Okay. In this setup, when we're talking about non-Gaussian processes, inputs are the analog of external inputs to the neural network are analogs of external space or space-time points. The kernel is the analog of the free or exact propagator, depending on details. The network output f of x is the analog of the interacting field, and the log probability is the analog of the effective action. Okay. There's a lot to say here. in the interest of time, what I'll just make the basic physics point that you could run the standard Wilsonian type of paradigm in this context, where you're trying to come up with some non-Gaussian additions to your effective action that are going to correctly model, in a phenomenological sense, the what's happening in the neural networks, statistically speaking. And what you would do is determine the symmetries respected by the system of interest, which I'll say a lot about. You would fix an upper bound on the operator dimension, and then you would write down all operators up to that dimension that are consistent with the symmetries. You would run a normal Wilsonian type of approach. Okay, but that's sort of physics background, and I want to talk about symmetries. I think this is the last slide before I get there. That once again, you can write Feynman diagrams for neural networks. In this case, I have turned on the non-Gaussianities. Lambda is the quartic coupling and kappa is the sextic coupling. And you can write down Feynman diagrams and equations in terms of kernels that represent in that statistical model of the neural network architecture that represent the correlation functions. Okay, so for the last part of my talk, I want to talk about symmetry. And this is something, a lot of you have heard some of the previous stuff here, but this is something newer from a paper that we submitted to NeurIPS a few months ago. And this is about symmetry. So if we're using effective field theory type of techniques to model neural network densities over functions, there's a question of what symmetries we should impose, right? So this is something we do all the time in physics. We have a bunch of particle physics experiments. The details of the interactions suggest that there are symmetries in the models that we should write down. And of course, in the models that we know and love, like the standard model, we know what those symmetries in the densities are. But there's a question for neural networks of how to do this. So you could be super pedantic about doing experiments, but we're going to promote another way here. And so this is one crisp theoretical result to prove that you can actually do things with these sorts of ideas. And there's a little more in the backup slides. And the basic idea is what we call in our paper symmetry via duality. Normally in physics, we use experiments to determine symmetries, some empirical data collected colliders or in condensed matter experiments, or in neural network context via drawing a lot of neural networks and collecting empirical data. Experiments can be used to determine symmetries, but what I'm going to suggest is that in cases where you have another duality frame in which to consider the theory, you can use theory to determine what the symmetries are. And the duality here is between parameter space and function space. The duality that I'll abuse is that parameter space and function space give two dual perspectives on the neural network. And what I mean is this. My correlation function is this. I'm writing this expectation value rather generally. It's expectation value of f of x1 through f of xn. Okay. And I'm going to write this in two different ways. On the one hand, we have one way of thinking about neural networks, which is composing a bunch of functions and sticking them together according to some parameters, theta, that have some parameter distribution. So one way to compute this expectation value is by thinking in parameter space and evaluating the expectation value in parameter space via integrating against the parameter space density. The density from which your neural network parameters are drawn from quite literally in your code that you fire up. The other is in function space, if there's some function space density PF, this is what we do in field theory, you compute your correlation functions in terms of expectation values integrated against the function space density, which is e to the minus action in field theory. So for example, in Gaussian process papers, the function space density is exactly the density associated with the Gaussian process. The inverse of the kernel appears up in e to the minus s, so it's e to the minus 1/2 double integral ddx dy, f of x operator f of y. And that's the function space density. And in general, it's quite different from the parameter space density, even though the architecture and the parameter space density together determine this. But what we don't know in general is what this object is. And that's what we're trying to figure out. So there's two ways to compute the correlation functions. So this is really nice. And in particular, when GP people compute the two-point function, going back to Williams' paper from the 90s, what they do is this way of doing it. But if you know the GP density, you can also just do this way of doing it. Okay, so there's two ways to compute, at least. So specifically, what we mean is that correlation functions are fundamental in the neural network system. Namely, correlation functions are just the higher moments of the function space density that defines the neural network. But they can be computed in either parameter space or in function space is the point here. And crucially, from physics, we know that, yes, we can talk about the symmetries of an effective action, but at the quantum mechanical level, we should really be talking about symmetries of correlation functions, right? So because I have this other way to compute correlation functions, I have another way to study the symmetries of those correlation functions by computing in parameter space, even if I don't know what the function space density is. So we can deduce symmetry properties of the function space description from the symmetries of the correlation functions. So the example that I have here, which is just one super sharp example, is that this is the SOD output symmetry of a neural network distribution, assuming linear output layer with invariant weights and biases. Okay. This G function is whatever is going into the linear output layer. So what I have is I have some transformed correlation function where some SO rotation acts on the neural network, some SO rotation acts on the neural network. I do the calculation in parameter space. I see that this R acts on this W and similarly on the B, but I'll focus on the W's. The R acting on the W, I will define to be W twiddle. So there is a change of coordinates happening on the parameters in this context. And this gives me dw twiddle. So I integrate over the tilde parameters now. There's a Jacobian factor, et cetera, et cetera. But crucially, if this distribution is invariant to this transformation, then what you can show at the end of the day is that you get the original correlation functions out. That is, the correlation function is invariant under the transformation. And for this is sort of the equivalent of like an ON vector model in field theory. So you or OD vector model rather. So the correlation functions are invariant shows that the system has a symmetry. Okay. So this is a rather general mechanism. Our paper has a lot of examples, and I'm happy to tell you about more of them. But the crucial central element is that there's a different duality frame in which to study neural networks. You can study them in function space, but because we think of our functions, our fields, as being composed of little sub-functions, little building blocks tied together by parameters, we can also evaluate the correlators here and use that to study the symmetries. So what I want to wrap up with, actually, how much time do I have?
I guess you'll have like 10 more minutes, something like that.
Okay, cool. So I want to talk about symmetry experiments. And what I want to ask is, does the amount of symmetry in the neural network prior affect learning? So in particular, I would point out that from this distribution point of view, how would we put that in statistical or in field theory language? What is being learned? So if I have 10 to the 500 trained networks, right? And I have no reason a priori to prefer one over the other, what you should do on any given input is compute the expectation value of f of x, where x is some fixed input, to see how well it does. The expectation value of f of x is the one-point function. So supervised learning is about the one-point function of the trained distribution. That is the central fundamental object. Famously, one-point functions in physics break symmetry, and that can be understood statistically too. So the process of starting with a symmetric neural network density and doing supervised learning and developing a non-trivial one-point function that represents the non-trivial predictions of the ensemble, that is breaking symmetry. And we want to understand in experiments how this comes out. And we'll test it in just single layer networks. What we're going to do is turn on means for the weights and or biases to see how it affects performance. So these are our symmetry breaking experiments. So MNIST is the handwritten digits. There's a slight variant of it called fashion MNIST, which isn't handwritten digits, but it's things like shirts and shoes and stuff like that. So the experiment details is that we have a single layer ReLU network with no bias. The width of the network is 50, and we're training with MSE loss. The learning rate is 1 × 10⁻⁴, and we've trained on fashion MNIST. So in physics language, what I'm going to do in this context, the weights and biases are drawn from some distributions with some means and standard deviations. Mu W is the mean of the output weight distribution. And when you study the details of the network architecture, you find that mu W being turned on, in general, will induce a non-trivial mean for the distribution itself. That is, it corresponds to turning on a vacuum expectation value. It corresponds to breaking symmetry. So as I turn on mu W non-zero, it breaks the symmetry at initialization of the function space density. And how many of those, because the output matrix is n by d out, or n by In this case, D out is 10 because I'm in fashion MNIST and there's 10 classes. So it's a 10 by n matrix. If I turn on k of those means, so I don't turn on all of them necessary. So for k of the rows, I turn on means. That will break SO10 to SO10 minus k at initialization. So I can control not only the strength of the breaking by the size of mu w, but also the subgroup to which I break. Okay. Crucially, I will point out at first that these results are one-hot encoded. So the class labels are labeled by a vector of zeros, except for one in one particular entry that labels the class, whether it's a shirt or a shoe or something like that. And so this is the plot of accuracy versus symmetry breaking. So as I break to smaller and smaller subgroups, that turns on k, or as I crank up the amount of breaking associated to the subgroup. So there's one way of breaking this direction. There's another way of breaking this direction. So as I break sort of along the diagonal, you can see that accuracy goes down and down and down. So for some reason, in this particular type of example, it seems that symmetry breaking at initialization is, whether or not you do it, is affecting performance of the trained network. Okay, so this is monotonically decreasing, and I emphasize that this plot has labels that are one-hot encoded. Okay, now when you think about it, let me suppose, for instance, that I take the case that k is equal to 10. In that case, the mean is turned on for all of the entries of the output at initialization. And when you think about that, if you turn on non-zero entries for all of them, but the label, the target, is all zeros except for 1, 1, in some sense, that's in the wrong direction. Namely, you're turning on non-zero entries for all of the entries in this case, when k is equal to 10, even though the correct label only has one non-zero entry. So if you'd like, that is breaking symmetry in the wrong direction. Something that is closer to the right direction is if instead of doing a one-hot encoding, you do something called a one-cold encoding, where you have a 0 at the spot of the class label and 1s everywhere else. Then if you turn on 10 non-trivial means, it's much more in the direction of the actual target label. So in this case, you're sort of breaking symmetry in the wrong direction. In this case, you're breaking symmetry in the right direction, so to say. And in this case, we actually have a non-trivial feature. When we break in the wrong direction, according to the one-hot labels, it's just monotonically decreasing as you break symmetry more and more. But when you use one-cold labels, what you actually find is that performance is maximized at some intermediate value of mu w. And what's special about this value of mu w, keeping in mind that the right answers that you're trying to hit onto is 1s everywhere except for 1, 0 in the vector. This value of mu w is the value of mu w that when you turn on the means is going to have the entries turned on somewhere close to 1. So it's turning it on in the right direction, but this is controlling the amount that it's turned on, the symmetry breaking. And in particular, this peak corresponds to being close to the class labels. And so it's not surprising that getting close to the right class labels, this is a good initialization. So this is just one example of how one might think about symmetry breaking in this context. I'm going to end in the interest of time, but the key conceptual result here is that supervised learning breaks symmetry in general if you have it in the prior. But whether or not it helps to break symmetry in the prior depends on the direction that you break it in. That if your class labels are in one direction of symmetry breaking and you break it in the other direction, it might actually lead to decreased performance to break symmetry. But if you break it in the right direction, it can actually help it. Okay, so break symmetry in the direction of ground truth labels. That's the upshot. There's add-ons about different GP breaking and symmetry during learning. But the takeaways here are that the backbone of quantum field theory is statistics. It is not algebraic geometry or topology, as much as we string theorists would like to say otherwise. Special quantum field theories happen to touch deeply onto algebraic geometry and topology, but the real math backbone is statistics. The path interval is defined by a density on functions, but the neural networks themselves are random functions drawn from some density. And what's kind of marvelous is that the large N limit of neural networks and also perturbative quantum field theory, as we teach it in courses, as I teach field theory, have nearly Gaussian densities, and the Feynman diagrams correspond to computing the higher moments of those nearly Gaussian densities in perturbation theory. And therefore, because of this common feature with respect to the statistics, similar techniques apply. Symmetries are here determined via correlators a la QFT, and this influences the network densities. And I didn't get to this final bullet point. So I'll just leave it there and say thanks for listening. And well, this is a great time to think about neural nets and field theory together. So, sorry to go a few minutes over.
Thanks a lot for the nice talk. So any question?
I have a question. Hi, Jim. This is George.
Hi, George.
Very nice talk.
Thank you.
So I completely agree with this point of view, actually, that quantum field theory goes back to statistics. Actually, it's Feynman's point of view. If you look at Feynman and Hibbs, the last chapter is really about statistics. And in particular, in that chapter, he talks about influence functions. So in other words, if I give you a system coupled to another system, people do that a lot in the coherence, and then you integrate out certain degrees of freedom, then you basically get some sort of effective action, right, upon integrating out degrees of freedom. And so that has a natural statistical interpretation. I was just wondering, what would that be in the context? Hey, Yang, can you mute yourself, Yang?
Sorry, I hear someone's very loud. I don't know who it is. It's not George.
Yeah. Anyway, so thanks. But anyway, so so that's one question about the neural network connection to quantum field theory. But the other one obvious question is that Feynman didn't realize that, but Wilson did, right? Yeah, you can define quantum field theory non-perturbatively, right, in terms of path integrals.
Yes.
But in principle, you have to regularize it, right? You put it on a lattice or something like that.
That's right. Yes.
And then you have to show, right, that the physics does not, the output data don't depend on how you regularize. In other words, the whole renormalization business. And so I was wondering, again, what would that mean in the context of neural networks? You know, what is UV? What is IR? What is integrating out? What will be the Wilson-Polchinski thing? You know, I mean, kind of some obvious kind of things from the quantum field theory side. Thanks.
So there's a lot of questions there. In terms of coupling two systems and potentially integrating things out, that's an interesting thing. So a basic fact, for instance, is that a sum of two Gaussian processes is a Gaussian process. So if I take one neural network architecture drawn from a Gaussian process and literally add it to another, right, I have some joint Gaussian process. And you can imagine trying to couple these things together in a way that there's some coupling parameter that you can do to try.
Environment. I mean, the issue would be the environment. What would be sort of the environment?
Yeah, I haven't thought much about that. That's a good question. As far as RG goes, there's many ways it could potentially arise. In the concrete context that we had, what we found, and then I'll try to address UV versus IR, and then maybe I'll mention Wilson-Polchinski. In the context of UV versus IR, in the context of our actual models, we write down some non-Gaussian action and hoping that it will correctly model what's happening in the neural network, and we do computations. And what we find is that there are divergences, and so we cut them off, yes. And of course, if you're matching to any experimental data, it's the experimental data matching to the theory at some fixed cutoff, right? And so that will give you some value for the Cordic coupling, for instance. And if you vary lambda, capital lambda, the cutoff, you'll see that the Cordic coupling varies. And so this is from our first paper. This is the Cordic coupling lambda. There's subtleties here, but basically the neural network data are the dots, and the slope is the best fit line. Theory predicts, when you do the beta function calculation, theory predicts that the slope is minus dn plus 4, and you find that the slope of the experiment very closely matches that. So you run sort of a standard renormalization type of argument there. There was recently a paper that just came out the other day by Harold Urban and collaborators. They're actually giving a talk at Northeastern next week, if you're interested, on using the Wetterick non-perturbative renormalization formalism in this sort of context. I understand their paper a little bit, but I won't try to do it justice here.
Okay, well, that was...
UV versus IR is another fascinating question, because taking classic cases of just interacting scalar field theory, for instance, local scalar field theory, the question of UV versus IR comes down to the question of what is position versus what is momentum, right? And one way to say it is that the Cordic coupling, integral d4x 5x to the fourth, that is a nice local coupling in position space. And what happens in that theory is that when you, of course, pass the momentum space, you end up with a maximally non-local interaction in momentum space, in the sense that there's multiple momentum integrals with delta function momentum conservation imposed at the vertex. And so if you'd like, normal notions of UV versus IR in field theory in that context have some perfectly local interaction that becomes some maximally non-local thing in momentum space, and that sort of is one definition of UV versus IR. In these contexts, there could be some non-localities lurking around in here, and that's something that we're currently actively studying. I have a lot to say there. Basically, the non-localities that are fundamental should be 1/n suppressed, but maybe I'll leave it there in case there are others.
Okay. I mean, one thing, if you can distinguish UV and IR, is that we have phenomena in quantum field theory that have both UV and IR interpretation, like anomalies. I mean, that would tie to your symmetry discussion. How about Wick rotation? That's my last. I mean, because in principle, we do Wick rotate because we do have causal structure, etc. Right? At least in flat space, we can do that. What would that mean, a Minkowski type of thing or causal structure in the context of neural networks?
In the context of neural networks, I actually don't have any idea about what it would mean. What I would point out, keeping in mind, that getting into axiomatic field theory is a whole other story, but there are these things called the Osterwalder-Schrader axioms. And
yes, of course.
Yeah, okay, good. So whether a neural network architecture actually gives rise to the density that satisfies those is obviously a very non-trivial check that one would have.
No, you can do Euclidean quantum field theory, obviously. You just have to satisfy Osterwalder-Schrader. Yeah, I agree.
But being guaranteed a Wick rotation to Lorentzian that is properly causal and whatnot, requires that these axioms are satisfied.
Well, there is another interesting thing in quantum field theory, which is this Epstein-Glaser causal perturbation theory that actually lots of people don't know, but some do, maybe you do, which is essentially if you do regularize everything by worrying about the causal structure, as you know, these guys being smart enough, they managed to actually get the finiteness to any order of perturbation theory. So, this is an interesting thing. I think Kevin Costello told me that people do understand David in the Euclidean case. So there is some understanding of Epstein-Glaser from the Euclidean point of view. So you can do that map for sure.
Very cool. Well,
anyway, thanks.
Thank you for the comment. Yeah.
Yeah, thanks.
Anyone else?
A question?
Hey.
Hi, Sven.
Hi, Jim. Thanks a lot for the talk. I have a question in the sense of the duality, how to understand it.
Yes.
And the question is as follows. So we're training here on with some input X. So that comes in some sense from some training data, which is drawn from some distribution.
That's right.
And typically, if I were to think about this, so question is, okay, so on the quantum field theory side, how should I think about this? And then the question comes later. The question is, when I think about the test set, or especially also about out of distribution samples that I want to throw into my network and make predictions out of this, how should I think of this in terms of the quantum field theory?
In terms of outer distribution perspectives, that is a great question. So let me first of all point out that you did indeed just introduce a third distribution, namely the data distribution from which the input is drawn is not p theta or pf. So what you would need to talk about is a particular training scheme. So for instance, if you do gradient descent in the infinite limit and you write everything in terms of the neural tangent kernel, there's an update equation that involves a sum over a batch, but of course that batch data is drawn from some distribution. So in the infinite limit, that turns into an integral.
Sorry, I didn't get the first comment. Sorry to interrupt. But no, in this integral, so why is there no integral over x in some sense, or where is it hidden in some sense?
There's no x is outside the integrals because you get to choose the x associated with the correlators. So if you would like, what you could do is you could integrate the correlation functions themselves against data drawn from the data distribution, but the correlation functions themselves are functions of the inputs. So like you could put actual images in concrete images for x1, x2, but here they're just variables, right?
Yes, but normally, so maybe it goes in a different direction. But if I think about the NTK kernel,
yes,
I would have an explicit dependence of that kernel on X. So on the data space it has been trained on.
The NTK kernel has right. It is true that it has a general variable dependence, but then in the actual dynamical equations, you evaluate that theta of x1, x2 on the concrete batch. That's right.
But it's not clear. Yeah. Okay.
Keep going.
Sorry, I
I'm
interrupted
happy to try to answer it. No, it's good. Yeah, my point is that this is just the fundamental. This is just the fundamental aspect of the statistics evaluated on arbitrary inputs. But then actual data indeed would be on concrete values of the x's. So when we run empirical experiments, of course, we have to choose certain x's and plug them in and then check the theory against the experiment. But yeah, but the correlation functions themselves are general functions of arbitrary inputs in the domain of the neural network.
Okay, I mean, this is, but in quantum field theory, like I would argue it depends a lot on what background we do quantum field theory on, what answer we're getting. And so, yeah. And that somehow should be reflected here as well. And that's kind of where this question is going.
I mean, gosh, yeah. I mean, I haven't thought much about. So you want to try to turn on a background dependence here?
Yes and no. I mean, there is a. I mean, I feel like there should be somehow an interpretation of what background, so what data space you're effectively calculating on.
Yes. And
that I don't see yet. Right. I mean, I see your point completely with saying, okay, I'm calculating correlation functions and so on, but
right.
This
maybe I should put it this way: the neural network prior itself, before training, is completely data agnostic.
Yeah.
Yeah. And that's what this is. So if you asked me something like, how would the quantum field theory description update under training? That's sort of a different question. But right. Okay. So maybe what I should say there is that this is the initialization parameter distribution and the initialization function space distribution. Something we're working on now is actually talking about how those update under training and how the description in terms of the field theory changes as you do that. But in the prior, there just is no data dependence, except for the fact that the prior knows about the domain that the data would be